Hey, welcome to I Flip for Math, Mathcast number 2, place value, number-based conversion. I'm Mrs. Gooding, and our quote tonight is by Erno Rubik. He's the inventor of the Rubik's Cube. You probably recognize that. You see it everywhere. You can see all those different examples of Rubik's Cubes, and my son loves Rubik's Cubes. He became determined to be able to solve one last summer, and he worked and worked and worked until he figured it out. He watched some videos too to help him, but he loves it. His favorite one right now is the 5x5, although he can do the 7x7 too, and he just became very determined. So Erno Rubik's quote, "If you are curious, you'll find the puzzles around you. If you are determined, you will solve them," is really appropriate and perfect for my son. It's also perfect for math, and the lesson we're going to do tonight is on number-based conversion. We are so familiar with base 10. We work in it all the time. We use it all the time. We think and we talk in base 10. And so in this lesson, we're going to have to stretch our brains and look at math as a puzzle, not as something yucky, not as something hard, not as something impossible, but a puzzle that we're going to have some fun figuring out. So I want you to be determined, and I want you to really enjoy solving these problems. So our learning goal tonight is to convert numbers from a base 10 place value system to other bases. There's some more pictures of Erno Rubik. He is from Hungary, and he has sold over 350 million Rubik's Cubes. It's the best-selling toy of all time. So if you invent a really great toy that people like, you might become famous just like Erno Rubik. Our individual lesson learning goals are to understand that in a base 10 place value system, numbers have a value that is based on the powers of 10. You know them, 1, 10, hundreds, thousands, and so forth. We're going to create a base 10 chart for a number just to illustrate that. It's something that's going to be so easy for you. You're going to think, that's what I learned when I was little. And that's right. And because you've been doing it so long, it's going to be a little tricky to get outside of that box. The next goal is to use the place value of other bases. So they are based not on powers of 10. They are not based on 1, 10s, hundreds, thousands. They're based on the powers of the number of the base. And you have to kind of think in exponents when we're talking powers, like 10 to the 5th power or 2 to the 3rd power. That's what we're talking about when we use the word powers in this case. We're going to create a base chart that will make it very easy for you to convert a number in a different base. Here is our vocabulary. It's pretty important tonight. Base 10 place value system. A place value system having 10 as its base amount. It is the numerical base most widely used by modern civilization. In each place value position, we use the digits 0 to 9. The binary system, we can tell what system that is because it has the term prefix bi in it, like bicycle, which has 2 wheels, or biped, which has 2 legs. The binary system is a base 2 system commonly used in computer science. Each position's value is based on the powers of 2. It uses the digits 0 and 1, and that's it. The octal number system, you can hear that word oct. Just like octopus has 8 legs, the octal number system is a base 8 system. It's commonly used in digital equipment based on the powers of 8. It uses the digits 0 to 7. The hexadecimal system. Now, the decimal system is actually the base 10 system, the decimal system, and deci means 10, just like when we're using the metric system. But when we say hexa, that means 6. And so hexadecimal would mean 10 plus 6, which is 16. The hexadecimal system is a place value system with a base of 16. It is used in modern digital equipment, computer science, and mathematics. It uses the digits 0 through 9, and then it uses the letters A through F to represent the digits 10 through 15. And I'll kind of go over that with you as we get to the challenge problem. Let's go ahead and look at our example. You can see some really cool things. One of the cool challenges that people were actually challenged to do is to create art using Rubik's Cubes. And so in that giant Mario artwork, you can hardly see the different Rubik's Cubes. But if you look down at the Superman artwork, you can see how they took the Rubik's Cubes and adjusted them so that the colors help to make the picture. And it's just really a cool idea, but you would have to own a lot of Rubik's Cubes. So for our first example, in using a base chart, we're going to convert the base 10 number 256 to base 5. So let's go ahead and see how we would do that now. So this is a very sloppy base chart, and if you were doing it, hopefully you would do a lot better than I do on the Bamboo tablet. But I wanted to show you what the number 256 looks like in base 10. So in base 10, what you probably haven't realized is that it is 10 to the power of 0, that first place value position, and then 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and 10 to the power of 4. Now, if those exponents look very unfamiliar to you, go ahead and watch my lesson on exponents that will help you to understand what an exponent is. But essentially, 10 to the power of 0, we're going to do last, because that's something that's even unfamiliar to a lot of students who are using exponents. So we'll start with 10 to the power of 1, which essentially means 10 one time, which is actually 10. And 10 to the power of 2 is not 10 times 2, but it's 10 2 times, which means it's 10 times 10, which is 100. You're starting to say, this looks familiar. 10 to the power of 3 is 10 times 10 times 10, which is 1,000. And 10 to the power of 4, which would be 10,000. Now, one thing this helps you to understand as a user of base 10 is that every time we move to the left, we're multiplying the base amount essentially by 10. So 10, the base amount 10 times 10 is 100, and 100 times 10 is 1,000, and 1,000 times 10 is 10,000. But that's the minimal amount that we can go right here, because you can't multiply 10 by any number other than 0 and get less than 10. So we start going backwards and dividing. So this is actually 10 to the power of 0 is 10 divided by 10, which is 1. And that's how we get our ones place value position. Now, if we were looking at the number 256 in base 10, and that's how you note that, base 10 in smaller numbers down below, we would say, well, how many groups of 100 are in 256? And you would say, because you're so familiar with base 10, well, 2. And then I would say, how many groups of 10 are in 256? And you would say, 5. And then how many groups of 1? And you would say, 6. Because 256 in base 10 is very easily represented as 256. Obviously, there are no groups of 1,000 in the number 256. Now, when we want to convert the number 256 into base 5, we set our base chart up the exact same way. We use 5 as our base, and then we use the exponent of 0, 5 to the power of 1, 5 to the power of 2, 5 to the third power, or the power of 3, and 5 to the fourth power. Now, I may not need to go quite that far. I'll know as soon as I've started doing my multiplication. So we remember that 5 to the 0 power is the same as saying 5 divided by 5, which is 1. So this is the ones place value position. But 5 one time is 5. So instead of having ones, tens, hundreds, thousands, we're starting out with ones, 5s. And then 5 to the second power means 5 times 5, which is 25. And 5 to the third power, which we could also just say 25 times 5, which is 125. And then I don't think I'm going to need to go any further, because 125 times 5 is going to give me a number much larger than 256. So I always start out with the number 256. And just like I would in the base 10 system when I said how many groups of 100 are in 256, I'm going to ask how many groups of 125 are in 256. And you can either divide that out by hand, or you could use a calculator to help you figure that out. When I divided it, I found that there are 2 groups of 125 in 256. And 2 times 125 is 250. So I went ahead and subtracted 250 from 256, and I got a remainder of 6. So I'm going to write that remainder right here, because now I'm going to ask how many groups of 25 are in the amount 6. Well, there aren't any. It's not possible. So I'm going to put a 0 there and move my remainder over here. How many groups of 5 are in 6? Well, 1. Because 1 times 5 is 5. And 6 minus 5 is 1. So I have a remainder of 1 that I'm going to write right here. Oops. Push my button on my pen again. How many groups of 1 are in 1? 1 group. That's right. 1 times 1 is 1. There is nothing left over when we subtract it. So when we are representing the amount 256 in base 10, I want to rewrite that somewhere. I don't know where else. Let's squeeze it in here with a different color pen so we can see it. 256 in base 10 is equal to, and we can't read it, 2011 because this isn't in the thousands place. And we don't read it 2 125ths either. We just say 2011 in base 5. See how I made that 5 smaller and slightly below it? That's how I would note that it's in base 5. So 256 in base 10 is equivalent to or equal to 2011 in base 5. Now let's see if you can write all of that down in your flip journal so you have that really neat example, and then we'll try it on some practice problems, which I'll go over with you because I know that all of these can be a little bit scary. So no matter what, I don't want you to let this frustrate you, because everything that you're learning while you do this is just going to be extra practice and extra stretching for your brain. It's not critical if you don't quite understand it, and we'll keep practicing it as we are in class. There's a crazy cube, and then a funny little meme. It says, "Oh, you solved a Rubik's Cube? That's cute," which would totally offend my son. Not really, but because he knows how hard it is to solve those. And you can see a really cool fountain in Erno Rubik's honor. And what I love is there's some diagrams behind him and some of the math behind creating the Rubik's Cube. So practice problem number 1, I'm going to have you use that base chart that I taught you how to make and convert the base 10 number 39 to base 2, which is the binary base system. So go ahead and try that. Push pause and then push play when you've done it to see how you did. It's kind of fun. It's okay if you don't get the answer correct, because everything that you try is simply strengthening your math brain cells. Okay, so I wrote 39 in base 10 and I made a chart. And when I'm converting to a binary base system or base 2, I know I'm going to need more spaces because there are a lot of groups of 2 in the number 39. The larger your number in base 10, the more positions you're going to need in your chart here. So let's go ahead and write 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, 2 to the fifth power, and 2 to the sixth power. I'm not sure how many of these I'm actually going to use, but we'll be ready. So starting here, we remember that 2 to the 0 power is 2 divided by 2, which is 1. Kind of a cool thought that if you were doing 2 to the negative 1 power, you would start going backwards and you would have 1/2. So that's kind of just a fun way of, you can keep going back in the other direction, and in higher mathematics you will. 2 to the first power is 2. 2 to the second power is 2 times 2, which is 4. 2 to the third power is 2 times 2 times 2, or 4 times 2, which is 8. I can keep multiplying by 2 as I move to the left. 8 times 2 is 16. 16 times 2 is 32, and 32 times 2 is 64. In each case, I've because I know that each place value system that I move to the left is times 2 times 2 times 2, that's a little faster than trying to figure out what 2 2 times 2 times 2 times 2 times 2 is, which is what 2 to the 5th power is. It's 32. So now I'm looking at the number 39 right here. And that's how many I have. I have 39. And I want to know how many groups of 64 I have in the number of 39. And you're like, you don't have any. It would be a 0. That's true. How many groups of 32 would I have in 39? I would have 1. 1 times 32 is 32. And then I subtract. It's like a division problem. 9 minus 2 is 7. So I have a remainder of 7 now. And I'm always going to write my remainder right below that next place value position on the chart. Now I ask myself, how many groups, this is always how many groups of 16 are in 7? And the answer would be 0. So I'm going to move that remainder of 7 over. How many groups of 8 are in 7? Again, 0. So I'm going to move that remainder over again. How many groups of 4 are in 7? And there is 1, because 4 times 1 is 4. And 7 minus 4 is 3. So I have a remainder of 3. Now I ask myself, how many groups of 2 are in 3? And there is 1. 1 times 2 is 2. 3 minus 2 is 1. I have a remainder of 1. How many groups of 1 are in 1? 1. 1 times 1 is 1. And now I'm done. Now, one thing I want to point out that I didn't mention in the others is when we're in a base 10 chart, you know that the largest digit you can write in any place value column is 9. If you had the amount of 10, you would carry your group of 10 over into the next column. So that's why we only use the digits 0 through 9, because 9 is the largest digit in the base 10 system. Now, in a base 5, you notice that the largest digit that we used in any column was 4. You will never have a digit greater than 4 in the base 5 system. Can you see what the greatest digit would be in the base 2 system? That's right, it's 1. 1 is the largest number you can have in the base 2 system, because if I had 2 here, I would move it over and put it in this column where I have a group of 2. So if I wanted to write this number, let's go to pink this time. If I wanted to write the number 39 in base 10 is equivalent to or equal to 1, because I start with the digit that has value, 1, 0, 0, 1, 1, 1, and then I put that little 2. 1, 0, 0, 1, 1, 1 in base 2. And that is how you convert the number 39 in base 10 into a binary place value system. Let's go ahead and try another one. So here's practice problem number 2, and also some diagrams that were used as Erno Rubik submitted his patent application. And you can see the inside mechanisms for turning all of the different cubes and all of the different figures. Kind of exciting. That's what it looks like inside a Rubik's Cube. My son takes them apart all the time, so I've actually seen those. So our practice problem number 2 is to convert the base 10 number 423 to the octal place value system, which is base 8. Go ahead and pause it, work that problem in your flip journal, go back and look at your examples if you need to, and then push play and we'll see how you did that. So I've already made your base chart for base 8 and I put the values in. And if you want to check with your calculator to make sure I wrote the correct values, you are certainly welcome to. But we are converting 423 in base 10 to base 8. So I'm going to start out asking myself the question, how many groups of 4,096 are in 423? And there are 0. It's too big of a number. And how many groups of 512 are in 423? Again, it's bigger than 423, so there aren't any groups of that. How many groups of 64 are in 423? I know that 64 will go into 423. It just so happens it goes in 6 times. So 6 times 64 is actually 384. And I'm going to subtract that from that 423. 3 minus 4, can't do it. 13 minus 4 is 9. 1 minus 8, can't do it. 11 minus 8 is 3. So I have a remainder of 39 left after I have my 6 groups of 64 and 423. So I'm going to write that right here under the next column. And I'm going to ask myself, again, how many groups of 8 are in 39? And I know there are 4 because 8 times 4 is 32. And I'm going to take that amount away. So 9 minus 2 is 7. So I have 7 left over that I'm going to write under the next column. And I'm going to ask myself, how many groups of 1 are in 7? And there are 7, because 7 times 1 is 7. And now I have no amounts remaining. So if I were going to rewrite this, 423 in base 10 is equivalent to 600, excuse me, I should not say that, 647. The habit is so strongly entrenched when we've done this our whole lives. 647 in base 8. I probably owe you a push-up for that one, for reading that number in base 8 like it was in base 10. Let's go ahead and try the challenge problem. It's time to challenge yourself. And I think that is probably the most challenging Rubik's Cube or type of cube that was ever invented if you're looking at that now. It's kind of a crazy, crazy cube. And I got to watch a video that showed them taking this cube apart so that you could see what's on the inside, and it is really cool on the inside too. So for your challenge problem, we're going to convert the base 10 number 1,342 in base 10 to base 16. Now this was the hexadecimal system that we were talking about. And the one thing that I want to remind you before you begin is that base 16 uses the digits 0 through 9 to represent those amounts. And then to represent the amounts 10 through 15, it substitutes A through F. So 10 is A, 11 is B, 12 is C, and so on. You can make a little chart for yourself if you need to. If you enjoy converting to different bases and you want to make up some problems of your own, because these are very simple to make up, and you want to practice putting them in different bases, you can check your work at the following web address. They've got a very, very easy converter to use, and you can enter any amount and find out what it would be, even in base 16, using that very strange way of representing numbers with the letters. And so you can try this and then check it. But I'm actually, for the first time, going to go over the challenge problem with you after you work it, because it is such a complex little system that I want to make sure that you understand it, and I don't want to wait until class tomorrow. So go ahead and try and work this problem, push pause, and then when you think you may have the answer, or you're sure that you have the answer, push play and we'll go over it together. Okay, so I've made your base 16 chart, and I've also gone ahead and filled in the values. For 16 divided by 16 is 1. 16 one time is 16. 16 times 16 is 256. And 16 times 16 times 16 is 4,096. And we're going to start out just the same way by asking ourselves how many groups of 4,096 are in 1,342. And there aren't any. It's too big. So now we're going to ask ourselves how many groups of 256 are in 1,342. And whether you work this out on paper or whether you use a calculator, it's still going to tell you 5. There are 5 groups of 256 in 1,342. 5 times 256 is 1,280. So I'm going to subtract that amount, because right here I have 5 times 256. I'm going to subtract that amount from 1,342. 2 minus 0 is 2. 4 minus 8, can't do that. 14 minus 8 is 6. 2 minus 2 is 0, and 1 minus 1 is 0. So I have a remainder of 62 that I'm going to move below the next column. So now I ask myself, how many groups of 16 are in 62? And what I know is that 16 times 2 is 32. And 16 times 4 is 64, which is too big. So 16 times 3. And 16 times 3 is actually 48. So I'll subtract that from the amount, 62. 2 minus 8, can't do that. 12 minus 8 is 4. 5 minus 4 is 1. Now, this is the fun part. So how many groups of 1 are in 14? And that's right, there are 14 groups of 1 in 14. And because we're in a base 16 system, that's okay, because the largest digit we could have in any place value position is 15. That's what seems crazy to people who are used to using base 10. Now, because if I wrote this number like this, it would look like 5314 base 16. But it's not, because these aren't in 4 different place value columns. They're in 3 different place value columns. So the way that we work that is we say if 10 is represented by A, and 11 is represented by B, 12 is represented by C, 13 is represented by D, 14 is represented by the letter E, and 15 is represented by F. Well, we have the number 14 here, so we're going to represent it using the capital letter E. So if I were to rewrite my original problem, 1,342 in base 10 is equivalent to 5, 3, and then instead of writing 14, I'm going to write the symbol for 14, which is a capital E. We would read that 1,342 in base 10 is equivalent to 53E base 16, which is really fun. You could come up with some really fun problems with lots of letters, but you have to do some experimenting with it, because not every problem converted to base 16 will have a digit greater than 9 in one of its place value positions, which will need a letter. So practice, try to make up some of your own. That would be my challenge for you. See if you can come up with some numbers that have lots of different letters in them as well as digits. Have some fun with that, and let's go ahead and go back to our Mathcast. Finishing up, go ahead and review your learning goals. Have you mastered all of them? Probably not. This is a really tough lesson, but it's really fun, and the more fun you have with it, the more success you'll have with it, really. Do you need to go back and review or practice again? Write down in your journal, are you at a 1, 2, or 3 level in your learning? Write down any questions that you might have still after completing the lesson. Crazy conversions, and they really are. You have completed Mathcast 2 number-based conversions. I can't wait to see you tomorrow.